So in today's lecture, we are going to discuss the Lsz reduction formula. So recall that so far, we have discussed several aspects of quantum field theory. We have discussed at length the endpoint correlation functions, so the endpoint correlation function is in general a function of n points of space-time, and it's defined to be the vacuum expectation value of the time-ordered product of n quantum field operators. Note that the vacuum in this definition is the true interacting vacuum, and the quantum fields in the argument of the time-ordered operator are Heisenberg fields. And if our state is not normalized, we have to divide it by the norm of the vacuum. But of course, we can take this to be normalized. So this is, we have claimed, is one of the most central objects in quantum field theory, and it contains, in principle, a lot of information about the quantum field theory. However, the reason why we have such faith in quantum field theory is because it's able to explain a lot of real-world data. And a lot of the real-world data come from scattering of particles. And as we have seen in a previous lecture, the scattering of particles is described by the S matrix. So we have what we call the S matrix. The S matrix elements describe the transition amplitudes. And this we saw how to calculate explicitly. So in quantum field theory, we want to connect the S matrix element with these endpoint correlation functions. We want to show how this can be obtained in principle from a knowledge of the endpoint correlation function, and therefore putting on a firm footing our claim that the endpoint correlation function does underpin the observables. So this is achieved through the Lsz formula. Lsz stands for Laban, Szymanczyk, and Zimmerman. So this is the Lsz theorem, and we are going to prove the Lsz theorem for today. So what is the Lsz theorem? Let's first discuss the statement of the Lsz theorem. The Lsz theorem tells us that the S matrix element taking us from the initial state to the final state, where the initial state is, say, has, so for the sake of argument, we're going to just assume that the initial state has two particles in approximate momentum mode. So the initial state is, say, Ka, Kb. And we're going to assume the final state has n particles. So it's described by K1, K2, dot, dot, Kn. And we are also assuming that these are bosonic particles. So then the Lsz theorem says that this is, the scattering matrix is equal to a bunch of integral operators, say d for x of a, e to the power minus I, ka x a, and then the differential operator, the Laplacian with respect to xa plus m squared. So this is the wave operator. So, and then similarly, we are going to have another integral operator for the second incoming particle. So there'll be an xb e to the power minus I kb xb del squared xb plus m squared. And then we get similar factors for the outgoing particles. But for the outgoing particles, there will be a difference. So, and the difference is that the exponential will have plus I. So we have e to the power I k1 x1 del squared x1 plus m squared. And then there'll be factors for each of these outgoing particle. So we put ellipses there, and then there's going to be an xn part. So there's a plus I kn xn del squared xn plus m squared. And all of this will be acting on the normalized endpoint correlation function, where the operators have the same argument as the integration variables. So this is the Lsz formula, or the Lsz reduction formula, and we will be proving this in today's class.